Hi, GeoData people. We are going to continue with investigation 3 today, and we're moving on to lesson 2. And this starts on page 143 in your workbook. So if you remember the last lesson, we were comparing opposite and adjacent sides of a triangle to the hypotenuse. We were writing ratios or fractions comparing those sides to the hypotenuse of the triangle. So we're going to continue doing that today. All right? And if you remember, we were talking about opposite over hypotenuse and adjacent over hypotenuse, and there's one combination we didn't do, which would be comparing the opposite to the adjacent. Well, we're going to keep using those ratios today, but instead of talking about the ratios, they have names, okay? So all these ratios are called trigonometric ratios. We are doing trigonometry, okay? You may have heard of that before, trigonometry. Okay, it's kind of a branch of geometry. It's a branch of math that works with right-angled triangles. And so these ratios have names. The first name, opposite over hypotenuse, is called the sine, and it's spelled S-I-N-E, sine. And when we abbreviate it, it's S-I-N. So even though the word looks like you'd pronounce it sin, we know that's an abbreviation for sine. So we write S-I-N, but we say sine, okay? The second one, adjacent over hypotenuse, has a name, cosine. And we abbreviate that COS. You don't pronounce that cos, you say cosine. So you write COS as an abbreviation, but you pronounce it cosine. And the last function is the tangent, and that is the opposite divided by the adjacent side lengths. Tangent, what do you think we abbreviate it as? T-A-N for tangent. You don't say tan, you say tangent, okay? All right, so here we have a diagram of a triangle ABC. Here's the right angle. Let's focus on angle A. So AB is the hypotenuse. It's the slanting diagonal that's opposite from the right angle. This side BC is the side that's opposite the angle A that we're interested in. And side AC is the adjacent side, the side that is adjacent or next to angle A. So sometimes we will refer to angle A as the theta angle. And theta is a Greek letter, and it's used to represent an angle, and it's super easy to write, okay? A theta, you just write like a capital O, and you just put a little swirl on it. So when you write the O, just keep going around and make a little dip on the top, okay? So that's how you write a theta. So the sine of theta would be the sine of angle A. Sine is opposite over hypotenuse. So in this case, it would be the length of BC divided by the length of AB, which is the hypotenuse, okay? So that's what I just talked about right there. All right, on the next page, 144, we'll talk about the cosine and the tangent. Same idea. The theta is angle A. We're still using angle A as our focus right now. Cosine is adjacent over hypotenuse. So in our triangle, the adjacent side was AC. The hypotenuse is AB. So that would be the ratio or the fraction that we would calculate as the cosine of angle A. Tangent, which is a new one for us, is opposite divided by adjacent. And again, we would take the opposite side of angle A, which was side BC, and we would divide it by the hypotenuse of that triangle, which the adjacent side of angle A, which was AC. All right, and we write that TAN angle A or TAN theta, but you would say tangent angle A, tangent of theta. So let's do some examples. It's always easier to use real numbers. So here is a triangle, PQR, and we are going to focus first on angle that's 53.2. That's angle P. So that's going to be our theta right now. When this is our theta, when this is the angle we're interested in, this is our opposite side. 3 is our adjacent side. And 5 is always the hypotenuse. That doesn't change. So the sine of 53.2 degrees, the sine of this angle would be opposite over hypotenuse, or 4 over 5, which is 0.8. The cosine would be adjacent over hypotenuse, 3 divided by 5, which is 0.6. And the tangent is opposite over adjacent, which will be 4 divided by 3. Sometimes we do it out as a decimal. Sometimes we leave it as a fraction. I'm writing both because I want to talk about the patterns, and you may see some patterns here. All right, and that would just keep going. What if we change our focus? What if we change our theta? Let's look at the other angle, the 36.8. So what if that was our theta? I'll change color so we can keep them straight. If this is our theta, the hypotenuse is still the hypotenuse. That doesn't change. But 3 is no longer, side PR is no longer the adjacent side. Now it's the opposite side to angle Q, right? And the side that's touching angle Q, the adjacent side, is now QR. All right, so you can see how they switched places. So now if we are focusing on that 36.8 degree angle and we want to calculate the sine, opposite over hypotenuse, opposite is now 3 divided by 5, which is 0.6. Cosine, adjacent over hypotenuse, is now, this side is the adjacent side. So QR, which is 4, divided by the hypotenuse, which is still 5. So that's 0.8. Now let's look at the tangent. Remember, it's opposite divided by adjacent. Opposite is 3 divided by the adjacent, which is 4. Okay, now look at the numbers. Do you see a pattern? Look at how when we have a triangle and these two angles are complementary, they make up 90 degrees, right? Because they're the 180 minus the right angle. So these two together add up to 90. Notice how the sine of one angle, 4/5, is the cosine of the other angle, 4/5. And the sine of that angle, 3/5, is the cosine of the other angle, 3/5. Right? So the sine and the cosine kind of change places. What happens with the tangent? Do you see a pattern with the tangent? See those crisscross? Look at what happens here. The tangent of one angle, 4/3, look at how it inverts for the other one. From 4/3, it changes to 3/4. Okay, this is not a coincidence. This will happen in any triangle when you have those two angles. The sine of one angle will be the cosine of the other, and vice versa. And that makes sense because the opposite side of this angle is going to be the adjacent side of the other angle, right? Okay, so that should not be a big surprise. All right. So the next couple of problems we're going to leave for you in the whiteboard chat. But I want to show you, I'm just going to make up a problem for you. We've got a little extra time, so I'm just going to hand draw this for you. So what if we have a triangle? I'll call it ABC again. So here's triangle A, B, C, and that's a right angle, right triangle. Okay, what if this was an isosceles triangle, and what if these were both 45-degree angles? All right, so those angle measurements were the same number, 45 and 45. Okay, so let's say, I'm making up these numbers now, so let's say this side length was 5. then this side length would also be 5, right? Because this is an isosceles triangle. And what would the hypotenuse be? Well, we can use a squared plus b squared equals c squared and figure out what that hypotenuse would be. The legs are both 5, so it's 5 squared plus 5 squared. So 25 plus 25, which is 50. And then we can square root it, right? And if we square root both sides, it turns out that c is about 7.07. We'll leave it at that. We'll round. Okay. So let's calculate some sines and cosines and see what happens. Sine, let's do angle A. Let's let angle A be our angle of focus. That's our theta, okay? So sine of angle A is going to be opposite over hypotenuse, which is 5 divided by 7.07. And if we do that on a calculator, funny enough, it's 0.707. Okay. What's the cosine of A? That's going to be the adjacent divided by the hypotenuse. Well, the side that's adjacent to A also has a length of 5. The hypotenuse is the same. So look at that. When we have a 45-degree angle, look at how they're the same. And what do you think happens with the tangent? So the tangent of that 45-degree angle is going to be the opposite divided by the adjacent. Well, opposite is 5, adjacent is 5. It's 1, okay? The tangent of angle A is 1. What do you think happens with angle B? So let's do that real quick right next to it. Sine of angle B is going to be opposite over adjacent. Oh, same thing, 5 over 7.07. Cosine of B is going to be adjacent 5 over 7.07. So again, 0.707, and the tangent, opposite over adjacent, 5 over 5. Of course, it's still 1, okay? So in an isosceles right triangle, both of the angles are 45, so they're the same, and the sine and the cosine are going to be the same number. In fact, they'll always be 0.707. The tangent will always be 1 because the opposite and adjacent sides are always the same length, okay? You're going to see this in a later lesson, but I just thought that was a nice example to include at the end of this one. So that's it for today's lesson, you guys. And now you can go back to your whiteboard chat and then do your exit ticket. Bye.